Those of you who have been diligently watching the videos, this is the final video you'll be seeing for a while. This is an opportunity for us to think a little bit about how we design these models relating inputs and outputs to achieve a slightly different purpose to help us to be able to predict or forecast into the future. So that's where we're going. Let's have a look at some PowerPoints to get ourselves on track for that. So using regression models for purposes of predictive analytics. The regression model is a linear process which relates some x variables to a y variable. In this context of prediction, what we want is some x variables that can be used adequately to predict y rather than necessarily to explain y, which is what a prescriptive model is about. And those variables are related to y through a linear equation with parameters beta 1 through to beta k. So when we use the language of prediction, typically we're talking about mostly about forecasting into the future. So often prediction and forecasting are aligned with each other, although that's not always the case. You might, for example, want to have some data on individuals, and you might want to use some characteristics of a person to predict whether or not they're likely to suffer from some disease. So that would be a slightly different application of prediction, but we're going to concentrate here on prediction as it relates to forecasting. So for us to be able to forecast into the future a value for y, we need to know what the values of x are going to be in the future so that we can use them to predict the values for y. So that kind of makes a slight difference to the way in which we formulate a model compared to what you might be doing if you're simply trying to explain y, where you just wanted to get the variables that make a difference to y. Here you need a particular set of x's that you can actually forecast. So when we come to our linear regression model and we choose x's that have that characteristic, that they are known into the future, then that kind of puts us in a world of a particular type of regression model, which we refer to as a time series model, and includes a particular set of x's that can capture the main features of y and therefore can be used to forecast y. We're going to look at one particular type of time series model that captures two basic features of a time series. So the idea of forecasting is slightly different to prescriptive analytics. In prescriptive analytics, we're trying to find x variables that explain why y takes a particular value or set of values, or why some people have more doctor's visits than others, or whatever it might be. In the case of predictive analytics, and particularly time series models, we're not so concerned about the why question. It's more about capturing patterns or features of the data. And if those patterns and features are there in the actual data, then we work on the assumption that they might continue into the future, and therefore that the model that describes the current patterns in the data can be a pretty good guide as to what you would need to know in order to be able to forecast the future. So the two characteristics of the data that we think are most relevant and interesting to us are the trend and the seasonality. So let me think for a little while about what those are. First of all, the trend in a set of data. What's that pattern about? Well, it's a long, steady pattern in how a series evolves over time. So the trend is the long-term pattern in data. So with sort of economic data, you're typically looking at having 15 or 20 years worth of data so that you've got a pretty clear idea about trend. What you're observing is not just something that's happened in the last year or two, but it's a long-term pattern. So here, for example, is a graph of the annual expenditure on healthcare for since 1985 to 2013. And you can see here there's a general upward trend. Probably it's a fairly poorly drawn line, but you get the idea that it's heading upwards. That's the general trend of the data. So what we want to do is come up with an x variable that would actually capture that trend. The model that we use is the linear trend model, and this is what it looks like here. So the particular choice of x that we make is a little bit unusual. Essentially, it's just a column like this here, where the first time period we takes the value 1, and then each year, in this case it's annual data, so each year we increase t by 1. So 1, 2, 3, 4, etc. So the reason we do that is that effectively that allows us, when we plot our time series like we did on the previous page, on this axis is actually time. And on this axis we've got y, in this case the amount of expenditure on healthcare. So as t goes along from 1, 2, 3, 4, etc., this model is assuming that we've got a straight line relationship between time and y. The intercept is beta 0, and the slope, time increases by 1, The slope gives you beta 1 here. That tells you how things are increasing over time. So that's the most basic kind of trend model that you could fit to a set of data. You stick a straight line through that blue line there. Okay, so that's the only trend model actually we're going to concentrate on this subject. There are more complicated ones that we could go on forever about, but just in this brief, 1 week introduction to time series models, that's all we're going to look at. The second component of the series that we might be interested in is seasonality. So if we have data that's a bit more frequent than just once a year, perhaps in this case here, we've got data which occurs every quarter. So there's 4 data points per year. The data often in these cases will follow a sort of a bit of a regular recurring pattern. For example, here we've got expenditure on food, and you'll see that there's a real sort of consistency about the jaggedness here. And if the data was, the graph was big enough, you'd see that you've got a peak, and then you've got basically 3 fairly low values, and then another peak. 1, 2, 3 low values, and a peak. 1, 2, 3 peak. So every year there's a peak quarter, and my guess is that quarter is probably the December quarter of each year, which would be October, November, December, because people spend a bit more money on lots of things, including food, leading up to Christmas, for example. So that's kind of a pattern, and you'll see that that same pattern occurs all the way through. So people are very predictable in terms of their behaviour in relation to how much they spend on food at different times of year. Way back in 1986 and still in 2012, 2013, there's 1 quarter of the year when they spend a lot more than the others. And the others tend to follow the sort of drop a bit further, start to climb, and then jump. Almost not 100% consistent, that pattern over those 3 quarters, but very predictable, really. So that's the seasonality in the data, which occurs within a year. So in this case, quarterly, but could easily be monthly data. So we want to be able to model that as well. And we model the seasonality with these things called dummy variables. And these dummy variables are a bit similar to things that you've seen before. There's 4 seasons in a year, quarter 1, quarter 2, quarter 3, and quarter 4. So we'll put in dummy variables for 3 of those 4 and leave the 4th one out and call that our base category. So quarter 4 is the base quarter. So the time series model here is essentially got a trend component to it and a seasonal component. There's the trend and there's the seasonal. Okay, so it's a fairly straightforward model. Just imagine instead of having quarterly data, we had monthly data. What we would have is a seasonal component that looks very much the same as this, except instead of just having 3 dummies, Q1, Q2, Q3, we'd have to have 11 out of the 12 months. So M1, M2, for example, up to M11. Or we don't have to omit the last one, we can omit any one of the 12 months, or in this case, quarters. Okay, so we set up our model like this and put in a bunch of dummy variables for the different quarters of the year and a column of numbers like that for the time trend, and that is how we estimate our trend model. So we basically run a regression of Y here on this set of columns as our X variables. When we do that, this is what the output looks like. And this is actually applied to this data here. So there is a trend to this data. You can see that it's generally, whoops, once again, I'm very poor at drawing straight lines. That's supposed to be a straight line through the data. But you can see there's an upward trend to the data. So our linear trend is going to capture that. But you can also see there's this within the year quarterly fluctuations, which the quarterly seasonal component is capturing. That's what the model looks like. We can now use that model to forecast in the future. But before we do that, it's not a bad idea to have a look at the coefficients and the p-values and make sense of the numbers that we've got here. First of all, look at the p-values. Everything's highly significant. So the trend is very much there. There is indeed upward growth happening in this series. It's a positive number here, so it's going up each quarter. And then likewise, the seasonal components here are very statistically significant. So there's variation from one quarter to the next without a doubt. That's what the p-values tell you. Now what about the coefficients? What do those numbers actually mean? I've just replicated that part of the output again here so we can see the numbers. Let's look at the intercept first of all. Let's remember the value of y that you get when you have all your x's equal to 0. In this case, what does it mean for t to be equal 0? Well, for t to be equal 0 is a particular point in time, isn't it? Because t simply counts out your quarters. So for in this case, T must be equal to 0 one quarter before this, which would be the June quarter of 1985. So essentially what we're saying is that this number here, $10,673 million when we put it in the units of Y, tells you the estimated trend value of the series when T equals 0. Oops, which says there is the fourth quarter, but in fact it's not the fourth quarter, it is the second quarter of 1985, sorry. Okay, so that's what the intercept means. The coefficient of T, well, that's the change in Y for a 1 unit change in X, as usual, but this X is a bit unusual. It's a time trend. It goes up by 1 unit each quarter. So this is essentially the model's prediction of the change in Y for a 1 unit change in X, which means for going ahead 1 time period, 1 quarter. So it's the estimated average quarterly growth in the series after adjusting for seasonality, in other words, controlling for all the other X's. And that's at $89.8 million. Okay, so that's the change in Y for a 1 unit change in X, in this case, in other words, for a progressing 1 further quarter. So that says to us that on average, sales are growing by that 89.8 million across the period, across the whole sample. Okay, per quarter. What do these things here tell us? Well, they're just like multiple category dummy variables that we've interpreted in previous videos if you've been watching others. Essentially, they're telling you how the quarterly expenditure on food behaves in this particular quarter compared to the base quarter, which is quarter 4. So in quarter 1 of each year, you spend 1169 million less than quarter 4 after allowing for trend. In other words, holding other X's constant, remember that language. In quarter 2, you spend 1299 less, and in quarter 3, you spend 990 less. Notice they're all negative. So as I suspected before, that spike, that little peak that you see each year in the data corresponds to the fourth quarter. The first, second, and third quarters are all lower than that peak, and hence all of the coefficients of all of the Q1, Q2, and Q3 are all negative. But again, once you see this, you can see that even if we're not using this model for prediction, we've learnt a great deal about the dynamics of behaviour of this particular set of data. We know that in an average quarter, things grow by $89.8 million. So if you have a quarter where things grow by $200 million, you know you're in great shape. That's way above average. If things don't grow at all, you know you're in bad shape. You're way below average. So that number itself is useful. Likewise, the seasonal fluctuations. You've got a very precise estimate of the average amount by which things fluctuate from one time period to the next. That's fantastically useful information for planning. If you want to plan the stocks that you have in your supermarkets so that you don't have anything going to waste, then the secret is make sure you're well stocked in December, or October, November, December, because that's when the peak sales are. We all kind of know that, but now we know by how much. How much more do you expect to sell in the fourth quarter of the year compared to the ones before it? And then how much of a drop do you expect in the first quarter of the following year, and so on. These numbers give us estimates which help us to make all those kinds of plans. So how do we use this model, though, for the purposes that we started out, which was to plan into the future, or to forecast, rather? Well, the answer is pretty straightforward. All you do is you make a prediction of all the X values, which is pretty straightforward, and then you plug them into the formula and calculate the forecast for Y. So let's suppose the data finished at the end of 2013. Suppose we wanted to predict what was going to happen in the first quarter of 2014. Well, in the first quarter of 2014, we know what T is going to be. It's going to be 115 because it was 114 in the previous quarter and it goes up by 1 every quarter. We know what Q1 and Q2 and Q3 are going to be because we're in the March quarter of the year. That's a 1 and that's a 0 and that's a 0. So we plug those into our formula here, the intercept plus 89 point whatever it was, which we've rounded off to 90 times 115, minus the coefficient of the Q1, 1169 times 1, minus 1299 times 0, and 990 times 0. We didn't have to write those two out because they're both 0, but we just wrote them out for completeness. And that gives us a forecast of $19,835 million. So you'll see that we're sitting here in December having sold about 22,000 and we're actually predicting that things are going to go down in the next quarter by about 2,500, and that's exactly what the graph told us. Every first quarter of the year there's a drop-off. Okay, and it tells us exactly how much we expect it to go down by. So all you do is just take the formula that comes out of the Excel output based on these coefficients here and plug in the appropriate values of these things into the formula, and out spits a forecast. Now, that's all very fine and sounds pretty straightforward, and now we've got a way of using our model to forecast. So what I want to do now is just pause for a moment and help us to appreciate the fact that the world is not quite as simple as I've just portrayed there, and that there are some things that we might need to do to try and sort of allow for a bit of extra complexity. And those of you who are enrolled in the subject who have attended or watched the live lecture on this material, you'll see plenty of examples of this. There's some real data. So here's small extra complications of our data compared to what we've been looking at so far. So you can see now that the data's got a similar pattern. It's got an upward trend. It's got a seasonal pattern. It seems to go up and down within the quarter years, as far as we can tell. But there's funny periods where things sort of get steep for a while and then flat for a while and then steep for a while. And then there's all these sort of periods here where something funny happens, where it sort of drops suddenly for a little while. So there's a bit of extra complexity that a simple straight line through the data and a bit of quarterly ups and downs is not going to capture. What we need to be able to do is to cope with nonlinear trends in this case. It's not a straight line. It's actually curving upwards exponentially. So we need some kind of way of doing that. So we need an extension on those lines. And we're not going to go into that now, but that's something that you've got more to learn about. We need to be able to cope with outliers with these funny drops like this, where all of a sudden it just drops and then comes back again, which has usually got an explanation. But if you don't allow for it in your model, it can sometimes cause pretty lousy forecasts. And then you've got the possibility of what we describe as structural changes. Somehow the series is journeying along on a particular level, and then, for example, if we're talking about expenditure on healthcare, suppose the government said, right, we're going to tax or we're going to reduce the subsidy on healthcare, so people have to spend more. So there's a big government policy change, and you've now got to start paying to go to the doctor or pay more for your medicines. Then you should see a one-off big jump in healthcare to a new higher level, and that would continue on into the future. That's a, quote, structural change that's imposed on us in that case by some sort of government policy. And that means that our data doesn't sort of follow a nice smooth pattern like we expect with our linear trend in our quarterly fluctuations, and we need to work out ways of actually coping with that. Now, that's all I'm going to say about those extensions, simply to say they're there. They require a whole set of extra tools that we haven't looked at, but hopefully you've got a little bit of a taste of the most basic bread and butter time series model, and can start if you do want to read more or learn more in the future to explore some of these extensions that are necessary. And at that point, I'm going to